I'm sure there'll be a few more people wandering in. Thanks to everyone for coming out, despite the snow. Can you believe it? Rain and snow. Winter has really started, and soon it'll be good snow. Anyway, thanks for coming out. Those of you who've been around the Ski Institute for the last several years, you'll notice that every once in a while there's a strange accent that another strange accent that sort of joins the group, and that's our Australian friends who have come on a regular basis, and Barbara and Peter Johnston are here again for a month. They've both been here for sabbaticals in the past, and we continue to collaborate with them remotely. They sometimes participate in meetings, although getting timing between Australia and the US is exceedingly challenging. We decided that one of the other of us has to be up at about 3 in the morning to make a meeting work. So we do our best. So we really like to take advantage of the opportunity when they're here to spend lots of time listening and talking and figuring out what we can do. The topic of this particular seminar, and again, between the two of them, they cover a lot of ground in the sort of area of applied math. But the topic of this particular seminar is sort of near and dear to a lot of our hearts. I think all of us in the simulation game have become progressively more aware of the need to quantify the level of uncertainty or confidence, if you want to see it the other way, in our predictions. And what's been heartening for me is to see that there are techniques emerging out of the math, applied math community to help us actually do this, so that we kind of can treat it a little bit as a consumer product and hopefully use it appropriately. And so it's really great to have people like Barbara here to tell us more about these kind of approaches and how we might use them, integrate them into our own simulations, and generate some notion of the uncertainty, which we really owe it to our true clients, who more and more tend to be physicians who are, God forbid, making clinical decisions based on the models we give them. So they deserve our attention. They deserve some estimate of our confidence in our predictions. And so Barbara will spend today's talk describing uncertainty quantification specifically in the domain of cardiac modeling. So thank you, Barbara, and the floor is yours.
Okay, good morning, everyone. Rob sort of grabbed my introduction there in a way. So I was going to say that in modelling, obviously we don't always know the parameters for our models accurately, and so it would be great to be able to put some kind of bounds on the effect of uncertainty in the inputs and what effect they have on the outputs. So today I'm going to use cardiac modelling as my vehicle for explaining things in this area. I'm going to look at uncertainty quantification, which is the idea that I just talked about, which is given some uncertainty in the inputs, what kind of uncertainty is in the outputs. But I'm also going to talk about sensitivity analysis, which is which inputs are the outputs most sensitive to. So there's kind of two aspects to it. Right, so if I push the right button, I'll push it in the right direction. Right, okay. I'm going to start with my collaborators because it might give you an idea of how I got into this area to begin with. So Peter Johnston and his graduate student Joseph Barnes from Griffith University, where I come from. 5 years ago, Peter came here to the Ski Institute on sabbatical, as Rob said, and he became aware of work that some people here in Rob's group, papers written by Sarah Ganessa and Daryl Swenson in the area of polynomial chaos expansion. And he decided that he would do some work in that area. So that's where that came from. And then last year I was on sabbatical, and the first couple of months I spent in Sheffield, the University of Sheffield, with Richard Clayton's group. And they're interested in Gaussian process emulators. And so that's where that came in. And then the second part of my sabbatical, I came here last year, and through Rob, I met Akil, who's sitting here in the front. And Akil said, you can do some of this stuff that you've been doing with the Gaussian process things in Sheffield, where I was. They were working, the people in Sheffield, on cell models, and I'd introduced it up to a tissue level model. And he said, you can do some of this stuff using polynomial chaos as well as Gaussian processes. And so that's where that connection came in. And I thought just at the start, I would show you this little picture here. This is the software that Sam Coveney in Sheffield wrote that does the Gaussian process stuff. And the name of it down the bottom there Gaussian process emulator for uncertainty quantification and sensitivity analysis. But Sam liked the idea of the emu here, and so his little symbol here is a little emu. So I thought you might like to see that. Okay, as an outline of what I'm about to do, I'm going to talk about the motivation behind the kind of cardiac modelling that I'm going to be doing, and that's just the vehicle today to show you different types of things to do with uncertainty quantification. I'm going to talk about the methods. So the methods are Gaussian process emulators, polynomial chaos expansions, and I'm also going to talk a little bit about partial least squares regression that I've also used. I'm going to show you the modelling that I do and the kinds of visualizations and quantifications that I've done in that area using those techniques, and some results of that. And then I'm going to have just a tiny discussion because I'm really no expert in this area. As you may have gathered, I've been doing this for a year, some of it, and the other people that I'm talking about are really the experts, but just some of my thoughts about how I've used the two methods, the two main methods, and what the difficulties or advantages, disadvantages of those might be, and finishing up with some future work that I have planned. Okay, so for the cardiac people here, I guess this is all familiar, but anyway, I have to start somewhere. So you can end up with myocardial ischemia if you've got reduced blood flow to the heart. It's the most common reason that people present to emergency rooms. If they do that, then clinically people conduct an ECG. And one way of detecting the ischemia can be changes in the ECG, and specifically its ST segment. They may not see any changes too. So the relationship is not fully understood, and so that's the area of my research. So here we have a normal ECG trace, and here's the ST segment, and here's depression in the ST segment that you might see, or you might see elevation in the ST segment associated with ischemia. The idea being that clinically what people would like to be able to do is find out where the ischemia is to localize it and how bad it is. So going back to what cardiac tissue looks like so that we can do some modelling, up here we have cardiac myocytes joined together to make fibres of cardiac tissue, and they join together to make sheets of cardiac tissue. And then if you look at the sheets of cardiac tissue when you're thinking about moving through the wall of something like the ventricle, those sheets of cardiac tissue actually rotate relative to one another. I'm telling you this because these are the parameters that lead to the model. So the electric current can travel more easily along these sheets of fibres, that's the longitudinal direction, compared with across the sheets of fibres transversely. And then, as I said, there are sheets of fibres, and so the current can actually travel between the sheets as well in the normal direction. So we've got three directions there. And most people who are doing this kind of modelling use the bidomain model. In this case, the tissue is regarded as having two domains, intracellular, extracellular. So by the time you put those 2 and 3 things together, you end up with 6 bidomain conductivities. And these are inputs to my model, where the subscripts tell you which domain and which direction we're talking about. Okay, so here's a very big table that you don't really need to take much notice of the content of the table. It's a table of the bidomain conductivities. So there they are across the top, the 6 of them that I was talking about. The ones that are in bold are the only experimental studies, fully experimental studies that have been done to measure those bidomain conductivities nearly 30 years ago. And you might notice that the values actually are only for 4 of the bidomain conductivities for those measured studies. They were also conducted in different animal models and under different conditions. And so the results that you might see here or here is quite a variation in the values for the conductivities. To do the modelling when there are only 4 conductivities, they assume that the transverse and the normal ones are equal. So if you look on the table, there are various more recent values there, but none of those are fully experimental. Some of them are completely theoretical, some are partly experimental. And there's a wide variety in the values, an order of magnitude at least in some of the cases. So there's a lot of uncertainty in those parameters. When I use them later, I use values that are based on more or less the means of each of those values. Okay, so just talking about uncertainty in general for models and cardiac models, it can arise for a whole lot of different reasons. Obviously, there's measurement uncertainty, like I was just showing you there. There's intrinsic variability maybe in the parameters. There's inter-subject variability between people. There's things that these bidomain conductivities can change with time as the ischemia changes. So we've got this uncertainty in the input parameters, and what we're interested in is what effect they have on the simulations that we get out. So there's two ways of looking at this, as I said before. There's uncertainty analysis. So when inputs to a model are uncertain, how uncertain is the output? And then there's sensitivity analysis. How sensitive are the model outputs to the model inputs? Now, people have traditionally attempted to quantify this kind of thing by using Monte Carlo methods, but they require thousands and thousands of simulations to sample the outputs. And the idea of the work that I'm going to be presenting today is to do it faster. So I'll be discussing two main methods, as I said before, Gaussian process emulation and polynomial chaos expansions. And as I said, there's a third one, partial least squares regression, that I'll mention. So in each of these two cases, the methods produce this thing called an emulator. And what that is a statistical approximation to the original computational model, the program. And it's fast running. That's the whole point. So it's kind of like a black box that you can put something into and get something out of once you've set it up. And it works fast. Both these two methods use sets of training data. By that I mean you have some model inputs, you run the model, and you get some outputs. And you don't have to do that too many times. The way that they use that data and how they set up the emulators is completely different. The advantage, as I already said, is that they provide a fast surrogate of the model and they reduce the computation time. And once you've got them, you can use the emulators to do the things that I've talked about before: uncertainty quantification, sensitivity analysis, and predicting the model output for a new set of inputs. So you've got this black box, you get a new set of inputs, and you can predict what the output would be, and you can put error bounds on that. So starting with polynomial chaos, it's not related to chaos theory, even though it's got that same word in the title. It's actually been around much longer, 1938. And the idea of the polynomial chaos is to represent the output of the model by a series of polynomials that represent the inputs. The choice of the polynomials depends on the probability distribution associated with the inputs. Since we don't really know anything special about the kind of inputs that I'm going to be looking at, we'll use uniform probability distributions, and therefore Legendre polynomials are the ones that go with those. The idea is then to use stochastic collocation. In this case, we'll use Clenshaw-Curtis with the training data to find the polynomial expansion coefficients. However, the more inputs that you have, the more training data that you need. And so methods such as sparse grid methods can be used to reduce the number of the integration space, and the method we use is the Smolyak method. So once we've got that and produced found our coefficients and so on, we can produce a mean output distribution and its variance and higher statistical moments. We can produce the sensitivity indices that I was talking about earlier, so how sensitive an output is to an input, and also interaction indices between the inputs, the sensitivity of that. And we can estimate model outputs from a given set of inputs. So as an example for polynomial chaos expansions, I mentioned that Peter Johnston got the idea of this from people here who were doing this kind of work. And so here's an example just to show you what you could get out before I show you my own work. So this is a heart in a bath. You can see that. Well, it looks like it's in a box, but it's in a bath. It's in a bath of fluid that simulates blood in this particular case. And the green discs are defibrillation discs. So it's a model of defibrillation. And if you solve the model, when you apply a current across the discs, the idea is to see what sort of potential gradient that you get out and see whether the heart can be defibrillated or not. So you need 0.6 volts per millimetre over 90% of the heart to defibrillate the heart. So we've got two examples here. The left-hand column is 150 millivolts across the paddles. This is 230 millivolts. We can produce a mean, as I said before, using the polynomial chaos and the variance. And this is a visualization, I guess. So it's just something that we can look at and see what's going on. So in this case, we need to get 0.6 millivolts because it's too small for you to see. I think we need this sort of mustard colour up into the red. So you can see that not very much of the heart would be defibrillated in this case, but in this case, it would be. And if we look at the variance, we can see where the gradient field has the most variance, which is in the tissue, and not so much in the blood. So that's a visual way of looking at this kind of thing. Another way, or the way that Peter also had some kind of quantification in this case was, I didn't say, but he had the 4 conductivities from, you remember the 3 sets of bold data that I showed you in the table before, the experimental ones? The idea was to vary those across between their maximum and minimums of those 4. So you needed 41 conductivity data sets to run the polynomial chaos in that case. And what he did was look at how many of those data sets would produce defibrillation, in other words, 90% of the heart at the right gradient field. And so with 160 millivolts, only one of those data sets did. And you had to go up to the 230 millivolts to get all of them defibrillating the heart. So there was a wide variety depending on the conductivities that you put in. So that's just an example of something that you can do with polynomial chaos. So moving on to Gaussian processes. This is work from the people in Sheffield, and they were looking at the Lua-Rudy one-cell model, and they're interested in the effect of the inputs, so these maximum conductances to the model, and the outputs in this particular case are just not over the whole picture of the heart or whatever, as it was in the previous case, but they're single outputs. And so the single outputs that they were interested in were various features of the action potential, such as its resting potential and so on, and the action potential duration at 90% repolarization, which is the one I'm just going to show you a picture for in a minute. So for each one of those outputs, and there were 8, they constructed an emulator, and I'll tell you later about how to do that. So an emulator is if we represent it by this equation here, the x's are inputs and the y's are the outputs of the emulator. And what we're trying to do is to match the actual results, which are produced by the model, the ones in this case where fs is the actual simulator, the model, and we want them to be approximately equal to one another. And how do we do this? We do this by fitting the emulator to the training data. The assumption is that the output surface is smooth. In this case, if f is a Gaussian process, which is a distribution over functions described by y equals f of x, then the outputs from the emulator are a probability density with a mean and a variance, which is what we want. We want to be able to quantify the uncertainty in the output. So you can write a Gaussian process, the function, in this way, 2 terms. The first term is a mean function, and the second term is a covariance function. And then what we're fitting to, in this case, are these betas. So there's one of each of these coefficients here, these hyperparameters, for each of the input dimensions to the model. In their case, there were 6 of those conductances. And then in the covariance function, there are also hyperparameters that quantify how wiggly, I guess you might say, the emulator is. So building the Gaussian process emulator involves choosing forms for those things that I was just telling you about. Okay, so here's an output, the APD that I was talking about a minute ago, and here's one of the inputs. And the black circles are training data. The emulator is mean, is the blue curve, goes through the training data. The green is 2 standard deviations either side of the mean. So you notice it goes through the training data at the points, but in the middle here where there aren't very many points, it's not constrained so well and we get more of a deviation from the mean. And so if we were to put an input distribution on our input value here of GK, then we can get an output distribution on that particular output parameter. Okay, so far I've showed you a couple of examples of how people have used the two methods I'm talking about, and now I'm going to talk about my own work. So think back to the person in the emergency room who's had an ECG and the ST segment, and we're interested in what affect the ischemic region and what parameters affect whether you get ST elevation or ST depression and the connection between the two. So the modeling's done with the bidomain model, as I said before, and the equation is there, the passive bidomain equation. We have intracellular and extracellular potentials in the tissue and the transmembrane potential distribution, the difference between them. These conductivities, these M's, these tensors, they contain those 6 bidomain conductivities that I was talking about earlier, the one from the big table. And they also contain fibre rotation, the angle that the cardiac sheets rotate relative to one another as you go through the ventricle. They're my inputs to the model. So 6 bidomain conductivities, fibre rotation. Also the depth of ischemia will be one of my inputs to the model. And the last one is related to the potential in the blood. Due to the boundary conditions, there's also a conductivity in the blood comes into it as well. Okay, what does my model look like? It's a model of the ventricle, the left ventricle, and it's quite, it's a simplified model. It's not a realistic heart. So it's a half ellipsoidal geometry. The blood's on the inside here near the endocardial surface. This is the wall of the ventricle, and this is the epicardial surface on which I'm going to be looking at potential distributions. The eye there is the ischemic region, goes partway through the wall of the ventricle from the endocardium towards the epicardium. Here are my values, my distributions on the parameters that I'm going to be using. They come from that table. The means are approximately those in that table that I showed you earlier for the conductivities anyway. And except for this first one, they're the mean plus or minus 50%. So they're my inputs to the model. Okay, so starting with polynomial chaos, I'm going to show you examples of both ways I've used both techniques. Starting with polynomial chaos, I vary the inputs across those ranges using stochastic collocation, solve the model for each of those sets of inputs. So I said in Peter's model earlier there were 41 sets of conductivities. In my case, depending on the level, the accuracy, I guess you might say, I've got 145 or a higher number of sets of model inputs. And then I solve the model and produce these distributions on the heart surface, these epicardial potential distributions, which I'll call EPDs because it's too big a mouthful. So for my 8 inputs, I've got 145 sets of integration points. I produce a mean EPD and its standard deviation using the potentials and the weights. It's just a weighted sum. Okay, so here's an example of some of the outputs. Now, bearing in mind that I was talking about a ventricle shaped like a half ellipsoid, what are these? These are polar plots where we've squashed the ventricle down so that the apex is at 0 in the middle. And what am I plotting here? So I've got all my 8 variables varying across their inputs, and these are mean distributions produced by polynomial chaos for different ischemic depths. So just a very narrow piece of ischemia right through to 90% of the wall. And what I'm interested in is what kind of distributions that I get out. So when the ischemic depth is very low, I should have said the white thing here is the ischemic region. I've got a minimum sitting over the ischemic region. Then what happens as the ischemia increases, a maximum moves over the ischemic region and the minimum moves outside the ischemic region to the border, and it moves down, see, round down here. And at the same time, the maximum is obviously increasing in value as the ischemia increases, and a second minimum is forming here on the other side of the ischemic region, so that we end up with two minimums. So the features are different depending on the degree of ischemia, but I've basically categorized this in three things that I'm interested in looking at. One is this minimum over the ischemic region, because that's something that people are interested in clinically. I'm interested in the second case, which is where there's a maximum over the ischemic region and a minimum beside it. That's case 2. And then case 3 is the rest of them, where you've got 2 minimums and a maximum. So that's what's on the next slide in the middle here. In the middle here, these are those means that I just showed you, the mean distributions. So for 10%, 20%, and 70%, the 3 different cases, 1 minimum, minimum plus maximum, maximum plus 2 minimums. And I've plotted the distributions where, remember with polynomial chaos, we can get the standard deviation or the mean as well. So I've plotted distributions where I've got the mean minus the standard deviation or the mean plus the standard deviation. And you can see maybe in this second case that the mean distribution falls into my type 2 case with a maximum here. But once we take away one standard deviation, we're in the other case, the type 1 case where there's only a minimum. Okay, so that was something with polynomial chaos that I've done just to get a feeling for what's going on in the mean distributions and how much difference standard deviation makes. Now try something with Gaussian process emulators. So in this case, I'm going to vary all 9 of the outputs, so ischemic depth as well as the 8 that I was doing. So there's the list of them up there. I use Latin hypercube sampling to produce the sets of input data to sample the input space and then solve the model for each one of those cases and produce the EPDs and their outputs. Now at this stage, or for this work, as far as Gaussian process emulators go, and what I knew at the time, I guess, is that you could only produce an emulator for each output. So I couldn't look at the whole distribution like I just did pictorially for the PCE stuff. I needed to pick out points and make that a value for my output. So on those particular, I should just go back probably, on one of these plots here, the things that I'm interested in are things like the maximum voltage over the where the maximum is and its position, and also the minimums, their voltages and their positions. And the position I just characterized as an angle from 0, 0 up to the minimum, like that. So they're the outputs that I'm going to be fitting emulators to, and I've called them max V and angmax and so on. But you remember I had 3 different kinds of cases, and I'm particularly interested in that minimum case where there's just this one minimum. And so I didn't want to look at the data as one big set. I divided it into 3 types of data and then fit emulators for each one of those so that I can see which parameters affect, say, that minimum, for example, separately. So I fit an emulator for each output to the design data. So that's, I'll show you a picture of it in a minute. As well as fitting a Gaussian process emulator, another way that you can look at the sensitivities, which is what I was going to get out of this, is to use partial least squares regression. And it's a bit like principal component analysis. You do the regression of the outputs on the inputs, but in this case, it aims to maximize the covariance between them. So I just use that as a kind of check on the Gaussian process stuff. So here's the design data. So if we're looking at an EPD of type 2, that's the maximum plus a minimum, and I'm looking at the value of the maximum, its potential, then I've plotted this max V, it's the same data in every case, against the fibre rotation, against the the ischemic depth against each of the input variables. And then I fit an emulator to each one of these sets of data. And so you can see, for example, in the case of the ischemic depth, that max V doesn't really exist once we get above about 40, 45 ischemic depth. Okay, so this is 195 values plotted against each input, and I fit an emulator to each one of those. And I do that by fitting it to a subset of the data. So you keep 10% of it as a check. And in this particular software uses a Gaussian covariance function and a linear mean. You check it against the test data, and I use this software that I showed you with the little emu earlier. And the things that I produced from the software are mean effect plots and sensitivity indices. Okay, so what are we talking about here? If we've got our model, y equals f of x for the x inputs, and if we pick a particular input variable, xw, which is normalized, then the mean effect is the conditional expectation of that output, conditional on the input variable. And the sensitivity index is the ratio of that I just showed you to the variance of the model output. So I produced sensitivity indices, the idea being to see which inputs have the most effect on the outputs, to which are they the most sensitive. But first I'm going to show you a mean effect plot. So this is a mean effect plot for, again, EPD type 2, the maximum plus minimum. What have we got here? We've got the various model inputs on a normalized scale on the bottom here. So we've got all our 9 inputs, and we're seeing what the effect is on this max V, the potential of the maximum in that particular case. The 0 here doesn't represent 0, it represents the mean of that particular value. So for max V, that's 0.22 millivolts in this particular case. And then we see that let's just focus on ischemic depth. As the ischemic depth runs across the range of inputs, values that I'm looking at in the input data, the effect is that max V increases. Now, that's not surprising. We saw that in the picture in the first place. And we see that that's a positive relationship. And if we were to look at GIN, one of the normalized conductivities, the relationship in that case is much less. It has less effect, and it's a negative relationship. Okay, so we can see what the effect of changing the model inputs is on the various outputs. Here are the sensitivities. Now, this is an enormous table. Again, you don't need to be trying to look at all the values. So these are the sensitivities of these particular outputs to the various inputs to the model. And these are the different types. So in type 1, we only get min 1, its voltage and its angle. For type 2, we have min 1 and the maximum. And then for type 3, we've got 2 minimums and its maximum. So if we just focus, the ones that are bolded are the ones that are more significant. And if we focus on max V type 2, because that's the one I just showed you in the picture on the previous slide, we can see that the ischemic depth has a positive, quite a strong effect on the maximum voltage, and we saw that in the picture. It also has an effect on the angle. Now you'll notice that all the values in that table are positive, and that's because the sensitivity indices are calculated with variances, and so we don't get a sign associated with them. So you can't tell, for example, that with max V here, and we look at GIN, which was that one I showed you, that really should be a negative relationship. So this is something that comes out of these particular type of sensitivity indices. As a general comment, you can see that fibre rotation and ischemic depth are the ones that have the most effect, and there's not really much effect of the conductivities in this particular case. And we're going to focus on fibre rotation and ischemic depth a bit more later. Just so that a bit later we're going to see something, I'll just point out that fibre rotation affects that first minimum, its position and its angle, but really doesn't have any effect on the maximums and the other minimum. Whereas ischemic depth has a really strong effect on the maximums and the second minimum, and some effects on that first minimum, but not as much as fibre rotation. So the next table is going to be exactly the same table, but constructed with partial least squares. And it's much smaller, so it doesn't look exactly the same because there are now minus signs, and that wouldn't fit on the slide with all the extra minus signs. So what you find in this particular case is exactly the same thing, really. You've got your fibre rotation affecting min1, you've got ischemic depth affecting exactly the same. So this is just a check, I guess, but the advantage of it is that they're signed so that we know whether the relationship is positive or negative. Okay, and this is a summary of the same thing where I've just put arrows. Now we're talking about the black ones in this particular case. The black ones are exactly what was in that table, the ones that were bold. So that's where I had all 9 inputs varying and what effect it had on the outputs. And then people are really interested in the conductivities and what effect they have on these kind of outputs. And it seemed to me that the fibre rotation, the ischemic depth were like swamping everything. And it might be interesting to see if we were able to hold them kind of constant, what effect the conductivities would have relative to one another at least. And so that's what the red ones are there, but they're not really particularly relevant in this case. Okay, so I said to you that, well, I've just shown you Gaussian process sensitivities. And when I came here last year, as I said, Akil said to us, well, you can do sensitivity things using polynomial chaos as well, not just Gaussian process. And he helped us. We worked on this together. And so to produce these sensitivities, you've already produced the coefficients to produce the mean and standard deviation plots. And so it's just a matter of using them to produce the sensitivity values as well. But in this case, the advantage over the Gaussian process stuff is that you can produce the sensitivities not just for a single output, like max V in this case or whatever, but for the whole distribution. So before I show you those, I just want to remind you where the salient features that we're interested in, the ones that I tabulated, so that we can look at the right place on the distributions. So let's vary the 8 inputs and take ischemia over this region. This is the disadvantage, I guess, of this, is that I can't pick out bits of the data like I did in the Gaussian process case so that I could just look at type 1 or type 2 or type 3, because I need all the data to construct the distribution at the end. So by choosing ischemic depth between 40 and 90, I can be pretty certain that I'm getting that type 3 case only. And I also repeated this, and I did it for ischemic depths 10 to 20%. Now that will be a mixture of types 1 and 2, and I can't really separate them. I guess I could do it for type 10%, and that would give me type 1, but I don't know how to get type 2 kind of on its own. Anyway, getting back to this one, that's what our mean looks like. We kind of saw that it was about form before. This is the mean distribution, and this is its variance. And so these are not sensitivities. This is actual epicardial potential distribution. The most variance is in the value of the maximum over the ischemic region. So that's what you would expect, because we're varying the ischemic depth over quite a long range. And we see here that there's some variance here to do with the development of the second minimum as well. So we'll just bear that in mind. Now, these are sensitivity plots now, different scale, and these are how sensitive the outputs or the output distribution is to these particular inputs. So they're like my sensitivity indices, but instead of for a single point, they're for the whole distribution. So fibre rotation and ischemic depth, they're the two, and a little bit GIL. Fibre rotation, all right, so which things does it affect? Well, it doesn't appear to affect the maximum, because the maximum in this case is above the ischemic region. It doesn't really seem to affect minimum 2 up here, but it does seem to affect the development of minimum 1, which is down here, and that's exactly what I found on that table. The thing is, with the table, I could look at the minimum voltage, but I could also look at the angle of the minimum. Well, this is over a fairly wide range, and that minimum does move down and around. So you might be able to say from this that it affects the angle. I don't know. And then if we move on to the ischemic depth and what effect it has, well, yes, it has an effect on the maximum, which is over the ischemic region. It has an effect on the development of minimum 2 and maybe its position because it's over quite a wide range here. Does it affect minimum 1? Well, it's kind of down around here, kind of like where this is. Maybe. So this is, it gives you different information. It's not so quantitative, but it gives you a lot more information if you can use it. So I don't know, this is work that's quite recent, hasn't been written up yet or anything. So I'm just showing it to you to show you what you can find out. One thing you could be sure about, though, is that it's not sensitive to the blood, to the transverse conductivities or the normal conductivities, and that agrees with what my table showed as well. And then one last one of these. This is, well, perhaps I should go back and introduce it and then tell you what it is before you see all these pictures. I'm going to focus on fibre rotation and ischemic depth because they're the two major factors that affect the outputs. And I thought I could use it to study something about my modelling. And so my model has various assumptions built into it. And say one of them is where I put the ischemic patch. Another one is how big it is. Another one is associated with the border zone between the ischemic region and the normal tissue and how wide that is. So I've produced sensitivities for each one of those cases. So here is the thing that we just saw on the previous slide. So fibre rotation sensitivities, ischemic depth sensitivities. I've looked at the wider border zone. Doesn't seem to make much difference. We get the same sort of sensitivities. I've looked at a much larger patch of ischemia, which is nearly twice as big. Doesn't seem to make much difference. We still get them affecting the main things that we were talking about. This one is more interesting. I've moved the ischemic patch, it's the same size, from here upwards or down the ventricle. And in this case, the mean distribution looks different. So it looks like that might be actually different. But what's really happening, I think, here is that this region here is just moving, well, I suppose I should say this one and this one are moving together towards the centre. So it's still saying the same thing, that fibre rotation affects the minimum 1 and that ischemic depth affects the maximum and minimum 2. Okay, so that's the end of what I was, give you an idea of the stuff that I've done with this. So I thought I'd just summarise that before I just discuss about the different methods. So far I've shown you using polynomial chaos to visualise means and standard deviations for the distributions. I've calculated sensitivity indices of particular outputs like max V or whatever to the inputs, and I've done that with Gaussian process and partial least squares. I've produced mean effect plots which quantify the effect of varying an input on the output, and that was a Gaussian process one. I've visualized sensitivity indices to inputs for the whole distribution, and that was polynomial chaos. I've visualized, now I haven't shown you this, but I've done it, visualized the effect of pairs of inputs on the sensitivities. So the combined effect of two of the parameters. And you can, I've done it with polynomial chaos, but it can be done with the Gaussian process approach as well. But I basically haven't used any of these methods for predictive purposes. Okay, so just some final comments, my thoughts about the different methods and using them. And like I said, I'm no expert and I haven't seen anyone sort of write up a summary of comparison. With the Gaussian process approach, it can be quite difficult to ensure that you've got a really good fit for an emulator. You're making various assumptions to get the fits of all those hyperparameters. And you can end up with that sensitivity table to the various inputs such that it ought to add up to 1. The sensitivity to each of the inputs ought to add up to 1. But if it doesn't, it can mean that you've got a poor fitting emulator, or it can mean that there's interaction between the inputs, which I guess you could then look into. With Gaussian process, I believe you need one emulator per output, but people who know far more about statistics and Bayesian stuff that I do seem to be extending this through various techniques to do more than that. The sensitivity indices in this case aren't signed, even though you can see the direction in the mean effect plots. You can use partial least squares to get sign sensitivities, and that's really easy. In Gaussian processes, the emulator can be used to quantify the uncertainty in an output given uncertainty in the inputs. PCE, polynomial chaos, is good for visualization of the mean and variance and sensitivity indices. Gives you lots more information, but it's not quite so quantitative, maybe, particularly that thing about the angles. I'm not sure about that. And you need to bear in mind that in both PCE and Gaussian process, the output surface is assumed to be smooth, no bifurcations. And I've heard people talk who are doing more the cardiac cell modelling kind of stuff, like I showed you in that Sheffield example, where sets of inputs don't necessarily produce an action potential. So you've got kind of a problem where in some cases you do and in some cases you don't get the output that you're looking for. So that's something to bear in mind. Just to talk about what I might be going to do in the future, I've produced for a more realistic heart a picture that mimics that first one I showed you, where you increase the ischemia through from 10% to 90%. This isn't a Gaussian process, it's just using the mean values from my table. But you get the same idea that there's a minimum. The ischemic region's sort of up here. A minimum over the ischemic region, then you get a maximum forming, and then as it gets deeper, you get the second minimum forming as well. And so you get a similar development, and so that's related to what I want to do in the future. So here are some possible future projects. I want to consider the effect of different representations. Now, I didn't really talk about the transmembrane potential, which represents the transition between the ischemic tissue and the normal tissue, and how one represents that. I want to look at that in the half-ellipsoidal model. I want to consider partial thickness rather than sub-endocardial ischemia. This is a topic close to the hearts of people here in Rob's group who have shown that it's not necessarily, or it isn't the case, that the ischemia starts at the endocardium, the inner heart surface, and moves towards the epicardium. And so it would be good to model that. I might like to use emulators in a different way, a more predictive sense, and this is something that we've been talking to Akil about. And I'd like to, having shown you the picture of the more realistic heart model, obviously I'd like to redo some of this work with a realistic heart model. And to do that, I need to be able to vary the fibre rotation. And kindly, Brett over here has done a lot of work on that and has a rule-based approach to that, being able to vary that, which hopefully will allow us to kind of repeat some of this work in that way. And that's me finished, I think.
All right, other questions?
I'm going to sit down for a second if no one minds.
Absolutely.
Yes, hello.
A great talk, by the way. So it looked like the fiber angle rotation and the amount of ischemia were the major determinants in the kind of error.
Yes.
But it seems like, I mean, with current MR techniques, can't these be easily quantified? And such that your models would be more, so you talk about a realistic heart model, could you include these more accurate measures?
Well, a realistic heart model will actually have a particular set of fibre rotations that the particular person or animal actually had. They can be measured. Well, you can, but that's just that particular person or that particular animal. The idea is to look at varying them more systematically and seeing what the effect would be if Brett knows. There's been studies in human hearts where they've looked at what the variety over a range of people is, and there's a reasonable range in the fibre rotation within normal human hearts. Yeah, fibre rotation isn't something that can be easily measured in a patient-specific. And the point is we don't know what the depth of ischemia is in a particular patient either. What we're trying to do is see something from the ECG that might tell us how deep the ischemia is, rather than the other way around. Oh, absolutely. That's the other project that I'm very interested in. I beg your pardon, sorry. It's very difficult. And no one's. Mm. Well, if somebody would give Peter and I some money, I've designed an electrode to measure these conductivities. Rob's group are quite happy to make the measurements for us and do the experiments, but we haven't got the money to build the electrode. Oh, have you got some?
I want to ask a related question because don't your results suggest that this fascination with conductivity, at least in this specific context, I'm talking about propagation modeling and lots of other cardiac modeling, totally important. But in this particular context, it doesn't actually seem to matter.
That's frightening, really, considering that the other thing I want to do is measure the conductivities. Yeah, I was really quite surprised. The earlier work that I did when I was at Sheffield was on a slab model rather than a half ellipsoid model, and I didn't do it in quite the same way, and I was focusing more on the conductivities and less on what was going on with the ischemic depth, or that was kind of fixed or whatever. And so I didn't realise till I did this that the conductivities appeared not to be as significant in this with the assumptions that I'm making as I thought they would be. Yeah. So. I guess if we do some more work with a more realistic model, then we might be more confident about the results. Mm. Sure. You mean the actual size and shape of it? Oh, I guess I could. I haven't, but I guess I could. Yeah. The only geometrical thing I've done is changing the size of the ischemic patch that I showed you towards the end, and that didn't seem to make much difference. I don't know. Yeah, I mean, well, yes, I've used a slab model geometry, which is vastly different from, it's just a slab of tissue versus ellipsoidal, and you get more or less the same results. I think that's a reasonable thing to say. So yeah, maybe the geometry doesn't make that much difference. Also, the realistic heart model, I mean, I haven't done the sensitivities and so on, but you can see that the general progression is similar in that case as well.
We are actually doing an experiment to get these sorts of questions by in the heart volume itself, gather more and more during episodes of ischemia. And do an exponential. That's working on this. Starting point. Then we start adjusting parameters like geometry. Rules are nice because they put us in a parametric way. Anyway, it stays more or less realistic. It's really exciting for us to see that this fiber orientation seems to matter. All the input parameters. Yeah, because that was all we could guess.
That's the thing. Yeah. I guess if you could measure something, but that's the point. We don't know anything about them, do we? No.
You mentioned border zone as well, and you changed the depth of the border zone. The depth of the border zone matters, but also the profile of potential variation within the border zone.
That's what I was saying. One of the that's that that I want to change. Yep. It's like sigmoidal sort of S-shaped variation, so quite steep, and that was the idea, to make it less steep.